Hello and welcome to today's lesson, which is a lesson looking at an introduction to the mechanics course on the A-level AQA physics course. So in today's lesson we're going to look at some basic principles which link the GCSE forces of motion topic to the A-level mechanics topic, which you will cover if you carried out A-level physics. So the first thing we're going to look at is we're going to try and understand the basics of mechanics unit in AS physics and see how it links in to the GCSE concepts. Now the first concept you've got to understand in mechanics is the idea of speed. Now speed is a quantity that measures the distance an object covers in a certain time, and there are many measurable speeds in the world, such as the walking speed, which is about 1.5 meters per second, the running speed about 3 meters per second, the cycling speed about 6 meters per second, the speed of a car about 14 meters per second, the speed of an aeroplane about 280 meters per second, and the speed of the Earth orbiting the Sun about 30,000 meters per second. Now, as you'll be aware, speed doesn't involve direction, so it's something we call a scalar quantity. But the speeds in all these journeys are very rarely going to stay constant. They're going to be an average speed. Now, the speed of humans can depend on many factors, like the age you are, the terrain you're on, the fitness you have, or the distance that you've travelled. Now we can calculate speed with the following equation. Speed equals distance travelled in meters divided by the time taken in seconds. And because as we know it's a scalar, it won't involve direction, but it has the units meters per second. So this is the equation we use to work out the average speed of an object. Now if we have constant acceleration and the object is starting from rest, the final speed is always double the average speed, because the average speed will be the middle value of speed for the journey. So when the start of the journey and the end of the journey, so from 0 to final, the average speed will be in the middle. Now if an object moves along in a straight line, the distance travelled can be represented by a distance time graph, which is a graph that plots distance on the vertical axis against time taken on the horizontal axis. Now it's one of the only graphs in science where you don't draw a line of best fit, you draw plot to plot, because you're looking at the journey of an object, not trying to measure the trend of variables. So the speed of an object can be calculated from the gradient of a distance time graph. So to work out your gradient, you do your change in your y value divided by the change in the x value. So in this instance, it's the change in the distance divided by the change in the time. Now when calculating the gradient, we always draw our gradient triangles on, as it shows the values that we are using, and the gradient triangle should be as large as possible, as the greater the range of values used, the more the reliable result. But this method could only be used if the object has a constant speed, because you'll get a straight line of best fit. So if the object is changing speed, that means the object's accelerating or decelerating. So therefore the line of the distance time graph will be curving. So if an object's acceleration, its speed at any particular time, can be determined by drawing a tangent and measuring the gradient of the distance time graph at that particular time. So if, for example, we wanted to work out the speed at 10 seconds in this particular journey, we would draw a tangent, which is a straight line that touches the curve at the point of 10 seconds, the wanted point, but if extended, does not cross with the particular graph. So we've got our tangent there at 10 seconds, and then to work out the gradient of the tangent, you draw your gradient triangle on your tangent and then repeat the calculation as previous. Now you'll notice a few things. So on a distance time graph, if you've got a straight line, the object must be moving at a constant speed. If you've got a flat line, the object is stationary. If the line is curving upwards, you've got acceleration, and if the line is curving downwards, you've got deceleration. Now you'll notice something. On a distance time graph, the line can never go downwards. That's because distance is a scalar quantity. It doesn't have a direction, so it can only increase. So it can't go down, because distance is how far an object moves in a journey. So even if it returns in the opposite direction, it is still increasing its movement. So the quantity that can change in terms of this is displacement, because that involves both the distance an object moves, which is measured in the straight line from the start point to the finish point of a journey, and the direction of that straight line. Now displacement is not a scalar, it's a vector quantity, so it has a direction. So if a distance time graph shows a line going downwards, or in fact a negative, it's not a distance time graph, it's in fact a displacement time graph. So there's a clear difference between distance travelled and displacement. Distance is a scalar quantity. It's a measure of the total length you've moved, whilst displacement is a vector quantity. It's a measure of the straight line distance from the starting point. So whilst they're both measured in meters, one has a symbol of d, distance, and the other has a symbol of s, displacement. Now, displacement can be expressed in terms of a magnitude and a direction, and the direction can be given as a positive or a negative, so +5 and -5. So we can link this into the terms for speed and velocity, because the velocity of an object is its speed in a given direction. So velocity is a vector. Velocity is the rate of change, not of distance, but of displacement. So to work out your velocity, it's the change in your displacement divided by your change in time. And once again, because velocity is a vector, we've got to represent the direction it's moving in, so we can do that with either a positive or a negative sign. Whilst speed is a scalar, it's the rate of change of distance. So whilst velocity is a change in distance over a change in time, speed is a change in distance over a change in time. So speed does not have a direction, so it must be a positive value. So velocity is a much more useful quantity than speed because it contains more information. So because velocity is a vector, we can actually determine the direction of motion of an object. Now, just to clarify something, any quantity in physics with a direction is called a vector, and we can illustrate direction with a positive or a negative side. Now, you can decide which direction is positive and which direction is negative, but they've got to be opposites of each other. So up is a plus, down must be a negative. Now, it doesn't matter which direction is defined as a positive or a negative, as long as it's kept consistent in the situation. So, for example, if we state right is positive, then left must be negative. If we state that right, then right is positive, left must be negative. If we state that up is negative, down must be positive. So it works through like that. Now, if an object's moving in a circle, then it can have a constant speed, but it must have a change in velocity, because velocity is a speed with a given direction. So if an object's moving in a circle, it's changing direction, there is a change in displacement. So as a result, it means it's change in velocity, so the object is accelerating, and then it links in as so. Now we can show how velocity changes in a journey with the velocity time graph. Now in these graphs, velocity is placed on the y-axis and time is placed on the x-axis. So what will the gradient of this graph show? Now again, gradient is your change in y divided by your change in x. So the change in velocity over the change in time, which is what we call the acceleration. So the gradient of a velocity time graph shows the acceleration of an object. So if an object is changing its rate of acceleration, well then the line of velocity time graph will be curving. So again, similar to before, if we want to determine the acceleration at a particular point of a curving line, we've got to draw a tangent and measure the gradient of the velocity time graph at that particular time. So again, what if we wanted to work out the acceleration at 10 seconds? Well, what do? We draw a tangent to the curve where it's just touching at 10 seconds, draw the gradient triangle on your tangent, and then work out your gradient value. Now again, let's think about this idea logically in this one. So these are the following sections on a velocity time graph. Now if a line has a constant gradient upwards, it must be constantly increasing its velocity, so it's got a constant acceleration. If the line is flat, then the velocity is not changing, so it's maintaining the same speed. Okay, an object will only be stationary if that flat line is along the x-axis, because you'll have a constant velocity of 0, whilst a line with a constant gradient going downwards must be decreasing its velocity, so it's got a constant deceleration. And if the line is below the x-axis, you've got a negative velocity. Now again, negative in a vector means the object's traveling in the opposite direction. Now if you calculate the acceleration of an object and it's negative, you aren't actually sure unless you are observing the object or you have seen the velocity time graph to see whether it's either deceleration or it's acceleration in the opposite direction. So to work out which one it is, you've got to actually interpret the velocity time graph. So when we're talking about acceleration, what do we mean? Well, an acceleration is the change in velocity over a certain time. So again, because velocity's got a speed and a direction, acceleration can either be a change in speed or it can be a change in direction, because acceleration, like a velocity, is a vector quantity. Now we can work out acceleration with the following equation: the change in velocity, or the final velocity minus the initial velocity divided by time taken. So acceleration equals change in velocity over time taken. It's just the same equation written in different ways. Now, as the acceleration is the change in velocity divided by the time, the units of acceleration are meters per second, or meters per second squared. So you pronounce that meters per second squared, but it can be written in any of those three ways. Now, just to clarify, something we'll look into later on in the course is that a fundamental rule of physics states that an acceleration must be caused by a resultant force. No resultant force, no acceleration. Newton's first law of motion. So, here, if an object changes speed, it must be changing velocity so it's accelerating. So a resultant force is carrying this out, which is the most commonly thought of method of acceleration. A negative acceleration could be a decrease in speed. If an object here is changing direction, therefore it's changing velocity, therefore it's accelerating. So once again, a resultant force is required to do this. And in this instance, a negative acceleration could be the object moving in the opposite direction. Again, you will only know which one it is, either change of direction or change of speed, by looking at the information in the question or the velocity time graph. Now again, to produce either a change in speed or a change in direction, a resultant force is needed. So just to clarify, in these velocity time graphs, a gradient is worked out by doing the change in y over the change in x. So in a velocity time graph, it's the velocity on the y over the time on the x, it's acceleration. But the area under a curve is the y-axis multiplied by the x-axis. So the area is the velocity times by the time, which is the distance travelled. So you can actually calculate the distance travelled by an object by splitting up the area under the curve into triangles, rectangles and squares, working out the areas of these shapes and then adding them together. So you split the shape into squares and triangles, you work out the area of the square, you work out the area of the triangle, you add the two together to get the total area. So in this particular example, we've separated our lines into our area into rectangles and triangles. We worked out the area of the rectangle, 10 times by 8, 80. Work out the area of the first triangle, a half times by 10 times by 4, 20. Then we work out the area of the second triangle, a half times by 10 times by 2, 10. So we then add up all three to get our total area of 110 meters. So it works through like so. Now, we can also have a velocity time graph with a negative section. It means the object's moving in the opposite direction. So we've got a negative idea because the object's moving in the other way to where it was originally. So you've got the distance moved in one direction and the distance moved in the opposite direction. So we've got the positive displacement on one side of the axis and the negative displacement on the other side of the axis. So this means to work out your total distance travelled, you would have to add the two areas because distance doesn't include a direction, it's a scalar, so it doesn't matter what direction it's moving, you would still add them. But if you wanted to work out the total displacement, you would subtract one from the other because they're in different directions to each other. So we can use this velocity time graph to work out if an object's accelerating by looking at the gradient. So if you've got a straight line, constant gradient, flat line, no gradient, and because the gradient of the velocity time graph is acceleration, the straight line gives a constant acceleration, the flat line gives no acceleration. And only a resultant force acting on an object can cause an object to accelerate. So on the straight line we've got a resultant force, on the flat line we've got no resultant force. So let's consider a velocity time graph for any journey, but the one you've got to really be aware of is that of an object under free fall or a fallen object. So an object falling through a fluid or like a liquid or a gas initially accelerates due to the force of gravity. Eventually the resultant force will be zero and the object will move at constant velocity, which we call the terminal velocity. So for an object to accelerate, it must experience a resultant force. So when an object falls for long enough, the air resistance acting against motion equals the weight acting towards the earth. This means there's no resultant force as the two forces cancel each other out. So the object does not accelerate, it stays at the same speed and direction, it's achieved terminal velocity. So in these stages, to an object under free fall is carrying out a journey. So in stage 1, when the object first falls, weight is larger than air resistance, there's a resultant force downwards, the object accelerates downwards. And the resultant force causes your acceleration in the direction of the resultant force, Newton's first law of motion. So as the object accelerates downwards, it's because the resultant force is acting downwards. So you've got your air resistance a lot smaller than weight. So you've got a resultant force. So that gives you a straight line because you've got constant positive gradient, constant acceleration. But as the object increases in velocity, the air resistance increases as more air particles are pushed out of the way per second. So it decreases the resultant force, it decreases the acceleration. So now your air resistance has got bigger, your resultant force is smaller, so you've still got acceleration, but it's a smaller acceleration because the resultant force and the acceleration are directly proportional. That's Newton's second law of motion. So as the resultant force decreases, the acceleration it produces decreases. So don't forget to talk about this stage in a fallen object's journey. So it's now accelerating but slow in its rate, so it's curving downwards slightly because the gradient of the line is decreasing and the gradient of the acceleration is decreasing. So the velocity is still increasing but at a slower rate. Eventually the air resistance is the same size as the weight, so the velocity stays the same, that's terminal velocity, they're both the same size, no resultant force, no acceleration because there's no resultant force, so it maintains the same speed with the same direction, so if the object's already moving, it'll keep moving. We call that concept inertia. Once again, Newton's first law of motion, which we represent with a flat line on a velocity time graph. So it's got a gradient of 0, so it's got no acceleration, so it's got a constant velocity, a terminal velocity. So there's no resultant force. So remember that here the weight has stayed constant, it's the air resistance that's changed in size. So for an object under free fall, when an object first falls, the weight is larger than air resistance, there's the resultant force downwards, so it accelerates downwards. But as the object increases in velocity, the air resistance increases as more air particles are pushed out the way per second. This decreases the resultant force and the acceleration. Eventually, the air resistance is the same size as the weight, so the velocity of the object stays the same. That's terminal velocity. But what could you consider you could measure for a fallen object? So you've got 5 quantities: displacement S, initial velocity U, final velocity V, acceleration A, and time t. Now we can place these different measurable values into different equations to fully describe the motion of any object. Now, so we call these equations the equations of motion, or the Suvat equations. So the Suvat equations can be used to work out values of an object moving when the object has constant acceleration or uniform acceleration, such as when it's free falling due to gravity. So again, near the Earth's surface, this value of acceleration is 9.81 meters per second. Other examples you could have are a plane taking off, or a train pulling out of a station, or a car on a motorway. Now again, we sometimes call these equations of motion the Suvat equations because those are the terms found in the equation. S, displacement, U, initial velocity, V, final velocity, A, acceleration, and T, time. Now again, remember, S stands for displacement, not for speed, and D is for distance travelled. So we already know the first acceleration, we already know the first equation of motion. Now, acceleration is change in velocity over time, so it's going to be final velocity minus initial velocity over time taken, or V minus U over T, which we can rearrange as to V equals U plus AT, an equation you memorised at GCSE. But then the second equation, because what we do is we start with this equation of velocity equals displacement over time. We make displacement the subject, so it's velocity times by time, but technically it's actually the average velocity times by time. So how do you work out the average velocity? Well, you do the start and the finish divided by 2, because I'll give you the average. So now our average velocity is U, the starting, plus V, the final, divided by 2. So now we know that actually displacement, or S, equals U plus V over 2 times by T, our second equation of motion. Now, with equations 1 and 2, we can then derive an equation which eliminates the term V. So what we would do is we substitute the first equation, V equals U plus AT, into the second equation, S equals U plus V over 2 times by T. So you sub the first part of V into that one, you collect the U terms together, you then collect the T terms together. This gives you your third equation of motion, S displacement equals ut plus a half at squared. Then what we can do is, if we rearrange equation 1 to make t the subject, so when we said v equals u plus at, well, t equals v minus u over a, we then substitute that particular value for t into the equation, in equation 2. So then we can multiply side by 2a. Okay, so it's 2as equals v plus u times by v minus u. So therefore it's 2as equals v squared minus u squared. So it's v squared equals u squared plus 2as, which is an equation given in your equation book at GCSE. Now, just to clarify, you don't need to memorize the derivation of these particular equations for A level. It just shows you where it comes from. This is called the first principles of an equation. I've explained where all the equations have come from. Now, any question can be solved if three of the variables are given in the question. So what you would do is you write down all the variables you have, you look at the one you're asked to find and see which equation you can use. But we can only use them for motion with constant acceleration. So our equations are v equals u plus at, s equals ut plus a half at squared, s equals a half u plus v times by t, and v squared equals u squared plus 2as. And it's actually a very common examination question to work out the acceleration by these particular equations and place it into the equation F equals ma to work out the resultant force an object experiencing. So how do you answer an equation of motion question correctly? So you write out the variables which are known in the question, you use this to correct the select motion equation, where there should only be one unknown variable in the equation chosen, place the numbers in the equation, ensure the units are in the correct form, simplify and rearrange the equation as needed. Then step 4, calculate an answer, place in the correct units with the correct significant figures, and remember our assumption that the acceleration has to be constant. So let's look at an example question. For a particular ball, you make the measurements that the initial velocity is 0.035 meters per second, the final velocity is 0.013 meters per second, the distance over which velocity changes is 0.30 meters. What's the average acceleration of the ball during this journey? So you write out the variables which are known in the question. You then select the correct motion equation where there's only one unknown variable. So in this instance, v squared minus u squared equals 2as, or v squared equals u squared plus 2as. It's the same equation. Okay, you then pop in the values into your question. So you go 0.013 squared minus 0.35 squared equals 2 times by a times by 0.3. You simplify each side. You collect the terms together. So you find out eventually that a equals minus 0.122331 over 0.6. You then work out what a is, and then you put the values in with the correct units and the correct significant figures at a equals minus 0.20 meters per second squared, which means the object is decelerating because it's a negative value. Now, we can link this into something called projectiles. Now, a projectile is an object which has undergone this free-fall motion that we just described, like with the ball falling just then. Okay, however, this time with the projectile, the object has an initial push at the beginning, then nothing afterwards. So whilst these objects have only the force of gravity acting upon them whilst in motion, they do have an initial velocity. So, for example, a javelin. For example, a bullet being fired. For example, a parcel being dropped. For example, a ball being thrown. All those examples have objects which have an initial push at the beginning, then no other force acting on them afterwards, only the force of gravity pulling them down. Okay, so the definition of a projectile is it's any object that only has the force of gravity acting upon it during its motion, and it has an initial velocity. Now, all projectiles follow the same three key principles. The acceleration of the object is equal to gravity, g, and only acts downwards. G is the only factor that affects vertical motion. The horizontal velocity of an object is constant because gravity does not have a horizontal component. It only works vertically downwards. So the horizontal and the vertical velocities are independent of each other. The horizontal velocity of a projectile doesn't affect the vertical velocity of the same projectile. So the third principle is one of the most important ideas in physics, that the horizontal velocity and the vertical velocity are independent of each other. That means all objects will fall at the same rate irrespective of their horizontal motion. This means a ball thrown sideways hits the ground at the same time as a ball dropped from the same height. A parcel from a moving car and a parcel from a stationary car will hit the ground at the same time, and it means an object thrown from a moving train hits the ground at the same time as an object thrown by a person standing still if they drop from the same height. The horizontal motion of an object will not affect its vertical motion. So in theory, a person can fire a bullet from a gun, and a person can drop a bullet, and if it is at the same height as each other, the bullets will hit the ground at the same time. Now, all objects are pulled to the ground by the force of gravity. So all objects have a downward acceleration of g. Now any horizontal projection experiences the same downward acceleration as any other object. This means horizontal motion doesn't affect vertical and vice versa. The only factor that can be interchanged between horizontal and vertical motion is time, because the time of motion is the same regardless of its vertical behavior or its horizontal behavior. So it's important when we consider the motion of projectiles. Let's consider the vertical motion of projectiles, the motion of an object going up and down. Well, to work out that particular value, you would use the SUVAT or equations of motion we just talked about previously, because there's only one force in the vertical direction, gravity, so it's a constant acceleration, 9.81 meters per second squared, the acceleration due to gravity. But if we consider the horizontal motion, well, there's no resultant force because gravity does not act in the horizontal, so there's no horizontal force acting upon the object. That's our definition. So therefore the acceleration is zero because there's no resultant force, so we can work out the velocity with the equation velocity equals displacement over time. That still works. So the only value which you can interchange between your equations of vertical motion and horizontal motion is the time taken, because it's the same for both components, vertical and horizontal. So it leads to our golden rules of projectiles. Number 1, horizontal and vertical motion is separate, consider them as such. Rule number 2, the only value you can swap between the horizontal and vertical is the time. Number 3, going up is a positive value, so therefore going down is a negative value. Rule number 4, there are no forces acting in the horizontal motion, so there's no acceleration due to Newton's first law, so only the speed equation can be used. Then finally, the only force acting on the vertical motion is acceleration due to gravity, so use that in your SUVAT equations. So how would you answer a projectile question? Well, step 1, you work out the time for the vertical motion using the SUVAT equation. And remember, A equals 9.81 meters per second squared. Step 2, interchange the time taken calculation into the horizontal motion equation. Then use the equation that velocity equals displacement over time to work out the value that you need. Now remember, our assumption in these calculations is that air resistance isn't present and the object's a particle. That's a posh way of saying that basically the only force acting on the object is gravity downwards. So let's look at a question on projectiles. So an object is released 50 meters above the ground from a hot air balloon which is moving horizontally at a speed of 4 meters per second. Calculate the velocity of the object as it hits the ground. Well, this is the vertical motion, so we can use the SUVAT equation. So like before, we find the correct SUVAT equation, we put acceleration as 9.81 and then we work out our answer. So we know that v squared equals u squared plus 2as. Now note we're using minus 9.8 because we define upwards as positive, and as the object's going down to the ground, we define acceleration as a negative. So we say v squared equals u squared plus 2as, where a equals minus 9.8, s equals minus 50, it's going down, and the initial velocity is 4, so we work it through to be 31.6 meters per second. It then says, what is the duration of the descent? So now what we can do is, because again it's vertical velocity, it's a vertical motion, it's the vertical idea, so we can use the SUVAT equation again. Well, now we know a equals v minus u over t. So t equals v minus u over a. We know a is acceleration due to gravity, minus 9.81. We've just worked out what our final velocity is, 31.6. We know what our starting velocity is, 4. So we can put those into the equation, and our time of descent is 2.8 seconds. Now calculate the distance the ball moves horizontally before it hits the ground. Well, now what do we know? Well, it's the horizontal motion, so we can use the equation speed equals distance over time. Okay, so therefore we can then use the idea that distance equals speed times by time. We know from the question that the horizontal speed is 4 meters per second, but what's the time? Well, because the time for the horizontal and the vertical has to be the same value by the rules of projectile motion, the time in the previous question is the time in this question, so it's 4 times by 2.8, so the horizontal distance moved is 11.2 meters. Note, which is not the same as the vertical, because the vertical and the horizontal do not affect each other apart from time. So, in this particular lesson, we've looked at the basics of mechanics. We've looked at the link with GCSE physics, especially the forces and motion topic, and we've started to look at ideas of projectile motion and the equations of motion, which are the top starting points for A-level mechanics. If you want to read up any further, my advice will look at things such as Newton's laws, momentum, and the ideas of work, energy, and power. I hope you've enjoyed this lesson on an introduction to mechanics, and it's whetted your appetite for studying A-level physics and the mechanics section in a bit more detail. Thank you, and have a lovely day.